Moving on in our discussion of factors and divisibility, we're going to learn something called the division algorithm. Well, here's a theorem that's going to underpin the algorithm we present later. For any integer n and for any positive integer b, there exists a unique choice of integers q and r so that two things are true. N is equal to bq plus r, but also r is bigger than or equal to 0, but strictly smaller than b. Okay, so n is any integer at all, positive or negative. B has to be positive. Then there's only one way to pick q and r that makes both of these true, but there does exist that one way. So there always exists exactly one way to solve both of those desired results. So we'll get into the proof in a little bit. But for an example, let's see how this plays out. For example, n is 38 and b is 4. So what we need to do is solve 38 is 4 times something plus r, where the r is bigger than or equal to 0, but strictly smaller than 4. Well, if q is 9 and r is 2, then n is indeed equal to bq plus r. 38 is 4 times 9 plus 2. But what if I tried to let q equals 3 and r equals 26? This is another true statement that 38 is equal to 4 times 3 plus 26, but this doesn't satisfy the requirement that r has to be smaller than b. 26 is not smaller than 4, but in this first statement, 2 is smaller than 4. So there are multiple ways to solve one of these if you don't care about the other. Okay. However, there is only one way to solve it where both are accomplished simultaneously. That's the content of the theorem. As an example, find q and r for when n is negative 10 and b is 4. So a lot of people would default to saying negative 10 is a multiple of 4, specifically negative 8, and then subtract 2. So q is negative 2 and r is minus 2. That's really what this statement here is trying to accomplish. N is a multiple of b plus something else. Negative 10 is a multiple of 4, and then take away 2 more. But this doesn't satisfy that r has to be bigger than or equal to 0. Okay, this is a common error to make the first few times you work through this. This r has to be non-negative. So the actual correct solution for n equals negative 10 and b equals 4 is that negative 10 is negative 3 times 4 plus 2. In terms of notation, if q and r satisfy both of the above, r is called the remainder, q is the quotient, and the notation is that n percent sign b is the remainder. Okay, so n percent sign b is the remainder when n is, quote, divided by b. And then n over b in these square brackets is q. Okay, notice I'm not actually writing anything that looks like this. Okay, we are not writing that. That is a fraction and it might not be an integer, and we want to only work with integers. This symbol altogether represents the q that satisfies this pair right here. Okay, so this symbol here, don't think of it as a fraction inside brackets. Think of it as one complete symbol that represents the quotient spit out by the theorem on this page. Okay. So rewritten in terms of these symbols, n is bq plus r, but q I rewrite with this symbol here, and r I rewrite like this, where r is in between 0 and b, where it could be equal to 0, but it can't be equal to b. Now the theorem stated that n equals bq plus r, where r is in between 0 and b, has a unique solution q and r. Before getting to the fact that the solution is unique, first we're going to prove that at least one way of solving that does exist. So for n being an integer and b being larger than or equal to 1, we're just going to show it's possible at least one way to find a q and an r that satisfy both of our desired results. We're going to do it in a few steps. First of all, n can be any integer, but let's at least prove it works for natural numbers, and we're going to prove that inductively. So if n is equal to 0, notice we're only trying to find some choice of q and r that makes these true, without worrying if it's the only possible way to do it. But if n is set equal to 0, just let q and r both be 0, and you get n equals 0, 0 equals 0, true. And 0 is in between 0 and b, so okay, also true. So our base case is satisfied. Well, now let's assume that there was a solution for n. It was possible to write n as bq plus r, where r is in between 0 and b. We want to find some pair of integers, possibly different ones, so that n plus 1 is b times q prime plus r prime, where r prime is in between 0 and b. Well, we assumed that r was in between 0 and b. We assumed that up here. So there's two possibilities. Since it's less than b, either it's exactly b minus 1 or it was even smaller than that. In the first case where r is b minus 1, since we assumed n is bq plus r, that's bq plus b minus 1. We assumed r was equal to b minus 1. Now if I add 1 to both sides here, we get n plus 1, and over here we just get bq plus b, which I can factor the b out of and call it b times q plus 1 plus 0. So we're able to write n plus 1 is equal to b times something plus something else. So set q prime equal to q plus 1 and r prime equal to 0. 0 is a perfectly acceptable choice of remainder. It's definitely in between 0 and b. In short, if n has the largest possible remainder, then n plus 1 has the smallest possible remainder. If n had remainder b minus 1, then n plus 1 has remainder 0. In the second case, where r is actually less than b minus 1, then I can simply add 1 to both sides here and get r plus 1 is less than b. So now just let q prime be the same as q and let r prime be 1 larger. Then n plus 1, well, n was bq plus r. So I can just move my parentheses around and get this right here. But since r plus 1 is still smaller than b, r plus 1 is an acceptable remainder, and I have n plus 1 is b times something plus an acceptable remainder. So whenever it's possible to write n in the desired way, it's also possible to write n plus 1 in the desired way. Okay. It's also possible to write 0 in the desired way, so inductively we've shown that every natural number can be written in the desired way. But what about negative integers? Well, if n is negative, then negative n is a positive integer. Specifically, it's a natural number. So if n is negative, negative n is a natural number and therefore can be written as bq plus r. Don't make the mistake of thinking that because this term has a minus sign in front of it, it must be a negative number. If we assume that n is negative, this is now a positive number. Okay, since this is a positive integer, I was able to write negative n equals bq plus r. If r happens to be equal to 0, then negative n equals bq. In other words, n is equal to negative q times b plus a remainder of 0. So if this positive integer has a remainder of 0, then this negative integer also has a remainder of 0. But what if the remainder wasn't 0? Okay, then I'm just going to pick this as q prime and this as r prime. Well, n is negative negative n. Negative n was bq plus r. Okay, bq plus r, but now I'm going to do a plus b minus b, which should cancel each other out. Okay, distribute this minus sign and do some factoring, and we get b times this plus that. So I have b times an integer plus a remainder. But since r was less than b, b minus r is bigger than or equal to 0. And since r was bigger than 0, b minus r is less than b. So this remainder is allowable. Okay, so therefore, since this positive integer had a way to be written in the desired form, this negative integer has another way to be written in the desired form. So we've shown that any integer can be written as bq plus r, where r is in between 0 and b, but why is there only one way to do it? Well, suppose there are, in fact, two ways. So I can write n as bq1 plus r1, but I can also write it as bq2 plus r2, where both remainders satisfy the required inequalities. Multiplying the last inequality by minus 1, right here, I have to flip all the inequality directions, and I get negative b is less than minus r2 is less than or equal to 0, which I'm going to add to that one right there. So if I take this inequality and add it to this one, I get negative b plus 0, negative r2 plus r1, 0 plus b. This inequality is strict and this one was non-strict, so overall we lose information and we have a strict inequality here. Okay, so similarly there. So negative b is strictly less than r1 minus r2 is strictly less than b. Well, n is definitely equal to n. I think we can agree. Therefore, n is equal to n. I remember we assumed n could be written in both ways. Okay, but moving some stuff around, specifically subtract r2 from both sides and subtract bq1 from both sides and then factor a b out, we get that right there. Therefore, b is definitely a factor of r1 minus r2. b times something is equal to r1 minus r2, so by definition, b is a factor of r1 minus r2. But r1 minus r2 is strictly in between negative 1 times b and positive 1 times b. So I have a multiple of b. B is a factor of r1 minus r2. It's a multiple of b in between 1b and negative 1b. So it must be 0b. r1 minus r2 must be 0. But that means r1 equals r2. So starting off by assuming I could write this in two separate ways, these two r's have to actually be the same number. So let's go back to an earlier line. Okay, specifically right here, if r1 equals r2, then this must be 0. So 0 is equal to b times q2 minus q1. The only way the product of these two values can be 0 is if one of them is 0. Either b is 0 or q2 minus q1 is 0. But we assumed b is bigger than or equal to 1. That's part of our initial setup way at the beginning. So this can't hold, therefore this does. If q2 minus q1 is 0, then q2 must equal q1. So if I started with two different solutions here, we showed r's are equal and q's are equal. So it's not possible to solve this in two genuinely different ways. Any two ways that you claim to have solved this desired setup will lead to the q's being the same and the r's being the same. So you can't have two different ways of doing it. Okay, so not only is it possible to find a q and an r that solve our original requirements, there's only one way to do it. So the proof is complete, and that kind of justifies our notation. If there's really only one way to solve n is equal to b times q plus r, where b is bigger than or equal to 1, n is an integer, and 0 is less than or equal to r is strictly less than b, then since there's only one way to do it, I can write this. And I can write this. And there's no ambiguity in the symbol because there was only one possible choice, so the equal sign is fine. There's not going to be multiple different choices here. Well, let's remark about the power of what we've just shown. Okay, so for any n, which is an integer, and b bigger than or equal to 1, we have n is equal to bq plus r, so bq is equal to n minus r. So this is just the theorem we just proved, but sort of rewritten. Okay, n is bq plus r. Remember, q is this square brackets around n over b, and r is just n% symbol b. And then I just move some terms around, okay, to get the b times the quotient on one side. So what this says is that b has to be a factor of n minus the remainder term. Up here we have b times q is equal to n minus r. b times this quotient is equal to n minus the remainder. So b is a factor of n minus the remainder. So the quotient can therefore be computed by subtracting the remainder off n and then dividing by b in the traditional sense. If b is actually a known factor of this result, then division isn't a problem because it's not going to result in non-integer values. So for example, compute 218 over 5. Okay, the quotient. Well, the remainder is 3. Remainder when dividing by 5 is something many people are kind of quickly able to do in their head. So if the remainder is 3, subtract that to get 215. And now I can simply do the traditional division that I would do normally because I know the result is going to be a whole number, 43. So the quotient, 218 over 5, is 43. Can we find our Q's and R's through an algorithmic approach? We'd really like to not have to think very hard. Okay, so the technique described above is pretty easy when we're trying to find remainders and quotients for things that we're used to dealing with, like division by 10, 5, and 2. Remainders, a lot of people know some tricks to find remainders when dividing by 10, 5, or 2. And you may even know some tricks for 3, 4, 9, or possibly even 11, but those are a bit less well known. But what if I'm trying to set b is equal to 7 or b is equal to 243? Well, then it's going to be a lot harder to just sort of quickly spot what the remainder is supposed to be. But here we're going to have an algorithm that's going to find both the quotient q and the remainder. Okay, so here we have it. And we'll work through it in detail a couple of times. This requires that n be a natural number. Okay, so notice that the input stage, b is bigger than or equal to 1, that's always required, but we're actually requiring n to be a natural number. The algorithm can be modified to account for negative numbers, but it makes it take up more space on the page and makes it look more confusing. Okay, so we're actually just going to set that aside for now. So here's that algorithm, and let's get our hands dirty working through it. Compute both the quotient 23 over 7 and the remainder of 23 divided by 7. Well, we start at our start node. We input n is 23, b is 7, which does satisfy our requirements that n is a natural number and b is bigger than or equal to 1. We start off by declaring q is 0, and now we move to our first decision. b is 7, q plus 1 is 1. Is 7 times 1 bigger than 23? No. Therefore, I increase the value of q by 1, so now q is equal to 1. Is b times 2 bigger than 23? No, it isn't, so increase the value of q to 2. Is 7 times 3 bigger than 23? No, it isn't, so increase the value of q again. Is 7 times 4 bigger than 23? Yes, it is. So I exit this loop, and now I output the pair of numbers, whatever q is, comma, n minus bq. So I output 3, that's my current value of q, then 23 minus 7 times 3. So in other words, I output the first number, 3, that's my quotient q. 23 minus 21 is 2, that's my remainder. Okay, so I would recommend that you actually try working through this with a couple other choices, 28 over 5, 31 over 6, etc., to find both the quotient and the remainder to get a hand on what's going on in this algorithm. Okay, this is only checking multiples of b, and you keep increasing what multiple of b you're checking until you finally pass the value you're interested in. Once you do, you have a multiple that's too large. So b times q plus 1 is actually bigger than n. So q, b times q, would have been the previous multiple that wasn't bigger than n. So that's your desired quotient, and then n minus bq is always going to be r. Well, if we have an iterative algorithm for computing the q and r, the division algorithm, can we have a recursive algorithm that does the same? Yeah, it's going to exploit the fact that if n is solved as bq plus r, I can subtract b from both sides and say n minus b is b times q minus 1 plus the same remainder. But if n is less than b, then I can set q equal to 0 and just say the remainder is n. If n is less than b, then that's already an acceptable remainder. Okay. So we're going to call the outputs of the algorithm the quotient q here and the remainder r here for the purposes of making the recursive call. And here's the structure. It just says, if n is less than b, the quotient is 0, the remainder is n, and you stop. Otherwise, compute both the quotient and the remainder for n minus b. Add 1 to that quotient, but leave the remainder the same. And here's your recursive call. It just says, if I know how to solve it for n, I know how to solve it for n minus b, but I can also work the other way. If you can solve it for n minus b, then working backwards, leaving the remainder unchanged, but adding 1 to the quotient, you can solve it for n. That said, this is a really convenient way to write a program. It makes for a very short written program, much shorter than the iterative algorithm on the previous slide. but it's really not how we're going to do it by hand. So for manual computation, we're probably not going to touch this. Also, just about any programming language actually has these quotients and remainders as perfectly good built-in commands that you don't need to write your own algorithms for. But hey, it's worth going over and seeing how they work.